Millions of people have crossed the Appalachian Mountains without realizing they are passing over one of the most puzzling geological discoveries made in recent years. A landscape long regarded as ancient, stable, and slowly wearing away has begun revealing evidence that challenges expectations about how continents evolve. Why would a mountain chain, hundreds of millions of years old, continue to move? Why are some sections rising while others are sinking at the very same time? Why do precise satellite measurements and seismic imaging suggest that powerful forces are still reshaping rocks once believed to have reached geological retirement? For generations, the Appalachian Mountains were treated as a symbol of Earth's distant past rather than its active present. Stretching for roughly 1,500 miles, or about 2,400 kilometers from the Canadian province of Newfoundland to central Alabama in the United States, these mountains rank among the oldest major mountain belts on Earth. Their towering peaks were once comparable in scale to today's Himalayas, before hundreds of millions of years of erosion reduced them to the rounded ridges and broad valleys familiar today. That long-held image of an aging mountain range quietly eroding away is now being rewritten. Scientists examining seismic waves, satellite observations, high-precision global positioning system stations, and deep images of Earth's interior have identified something unexpected hidden far below the surface. Instead of finding a completely inactive continental interior, researchers have detected evidence that parts of the crust and upper mantle remain remarkably dynamic. Even more surprising, different regions of the Appalachians appear to be moving in opposite directions. Some areas are slowly rising, while neighboring regions are gradually sinking. The rates involved are incredibly small by everyday standards, measured in fractions of an inch each year or only a few millimeters annually. Yet over thousands or millions of years, movements this subtle are capable of reshaping entire landscapes, redirecting rivers, altering drainage systems, and changing the elevation of mountain ridges. The discovery did not emerge from a single dramatic observation. Instead, it developed gradually as multiple scientific disciplines began revealing pieces of the same puzzle. Modern satellite positioning systems, capable of measuring movements smaller than the width of a human fingernail, started documenting vertical changes across portions of the eastern United States. At the same time, seismic tomography, a technique similar in concept to a medical computer tomography scan but using earthquake waves instead of X-rays, began producing increasingly detailed images of structures extending hundreds of miles beneath the continent. These images revealed variations in density and temperature deep within Earth's mantle that were not expected beneath such an ancient mountain belt. Some regions displayed relatively cold, dense material extending downward, while neighboring areas appeared warmer and less dense. Such contrasts influenced the buoyancy of the crust resting above them. Understanding this process requires looking far beyond the mountains visible today. Earth's outer shell consists of rigid tectonic plates floating atop a hotter, slowly flowing mantle. While plates move only a few inches or several centimeters each year, those seemingly insignificant motions accumulate over immense spans of geological time. The Appalachians owe their existence to a series of colossal continental collisions that occurred between approximately 480 million and 270 million years ago. During those events, ancient ocean basins disappeared as tectonic plates converged. Fragments of volcanic island chains slammed into North America. Entire continents eventually collided, squeezing enormous volumes of rock upward into mountain ranges, rivaling any on Earth today. Those collisions culminated in the formation of the supercontinent Pangaea, when most of Earth's landmasses became united into one enormous continental assembly. Immense compressional forces folded, faulted, and metamorphosed rocks across what is now eastern North America. Eventually, that supercontinent began breaking apart roughly 200 million years ago. As the Atlantic Ocean opened, North America drifted westward, leaving the Appalachian Mountains far from any active plate boundary. Compared with tectonically active regions like the Pacific Ring of Fire, the eastern United States entered an extended period of relative geological quiet. Quiet, however, did not necessarily mean motionless. Earth's interior continues responding to processes initiated hundreds of millions of years ago. Dense sections of the lithosphere, the rigid outer shell, consisting of the crust and uppermost mantle, can gradually detach from the material above them. This process, known as lithospheric removal or delamination, changes the balance of forces acting on the surface. Imagine removing a heavy weight attached beneath a floating object. Once that weight disappears, the object naturally rises. Scientists believe a similar process may be occurring beneath portions of the Appalachian region. If dense mantle material has peeled away and sunk deeper into Earth's interior, the remaining lithosphere becomes more buoyant, allowing the surface above to slowly uplift. Yet this explanation alone does not solve the entire mystery, because uplift is occurring alongside measurable subsidence elsewhere. Some valleys and coastal regions adjacent to the Appalachians continue experiencing gradual sinking. In certain locations, this downward movement partly reflects the lingering effects of the last ice age. During that period, enormous ice sheets covered much of northern North America. The tremendous weight of ice, reaching thicknesses of several miles or several kilometers, depressed Earth's crust beneath them, while pushing surrounding regions upward like the edge of a compressed mattress. As those glaciers melted beginning roughly 20,000 years ago, the crust beneath the former ice sheets started rebounding upward. Areas located farther south, which had previously been pushed upward around the edges of the ice mass, have instead been slowly settling downward. This process, known as glacial isostatic adjustment, continues today because Earth's mantle flows extremely slowly, requiring thousands of years to fully respond to changing loads. However, glacial rebound cannot account for every observed pattern across the Appalachian Mountains. Some regions displaying uplift lie well beyond where ice loading effects alone would predict. Likewise, certain sinking areas exhibit behavior suggesting additional mechanisms operating deep underground. This combination of surface observations and deep Earth imaging has encouraged scientists to explore the possibility that multiple geological processes are acting simultaneously. Ancient tectonic scars, mantle flow, lithospheric density variations, erosion, sediment transport, and post-glacial adjustment may all be interacting to produce the complex pattern of rising and sinking observed today. Rather than representing a dormant relic of Earth's distant past, the Appalachian Mountains increasingly appear to be part of a living geological system that continues evolving despite its extraordinary age. Every new seismic image, every improved satellite measurement, and every refined computer model adds another piece to a puzzle stretching from the surface forests and ridgelines down through tens of miles or scores of kilometers of continental crust into the slowly moving mantle below. Instead of asking whether these ancient mountains are changing, scientists are now trying to determine why those changes are occurring differently from one region to another. The answer may reshape understanding not only of the Appalachians themselves, but also of how supposedly inactive continents continue evolving long after the great mountain building collisions that created them have faded into Earth's deep past. Evidence supporting the idea of an active Appalachian interior has grown considerably as advances in seismic imaging have allowed researchers to peer farther into Earth's mantle with remarkable clarity. Unlike conventional photographs, these images are constructed by analyzing the speed at which seismic waves generated by earthquakes travel through the planet. Every earthquake sends multiple types of waves through Earth's interior. As those waves pass through rocks of different temperatures, densities, and compositions, their speeds change in measurable ways. By comparing thousands of seismic recordings collected from monitoring stations across North America and around the world, scientists can build three-dimensional maps revealing structures hidden hundreds of miles or hundreds of kilometers beneath the surface. Those maps have uncovered one of the most intriguing features associated with the Appalachian region. Deep below portions of the mountain chain, researchers have identified unusually dense zones extending into the upper mantle. These structures differ from the surrounding mantle in both composition and seismic velocity, suggesting they represent remnants of ancient tectonic processes rather than ordinary mantle material. One explanation attracting considerable scientific attention involves the slow removal of parts of the lithosphere. The lithosphere includes Earth's crust together with the rigid uppermost mantle, forming the tectonic plates that move across the planet. Although this layer behaves as a solid over short periods, geological time allows gravity and heat to produce gradual changes that would seem impossible on a human timescale. During the enormous continental collisions that created the Appalachians, the lithosphere beneath eastern North America became unusually thick. Enormous compressional forces stacked slices of crust on top of one another while also forcing dense mantle rocks downward. This thickened root helped support mountains that were once several miles or several kilometers taller than those seen today. However, geological roots do not necessarily remain stable forever. Dense mantle material can become gravitationally unstable if it cools sufficiently or undergoes mineral transformations that increase its weight. Eventually, that dense material may begin peeling away from the lighter crust above. Scientists often compare the process to a heavy drop of syrup slowly separating from the underside of a spoon. Once detached, the dense material sinks into the deeper mantle, while hotter, lighter mantle gradually rises to replace it. This process fundamentally alters the balance supporting the surface. When the dense root disappears, the remaining crust becomes more buoyant. The result is gradual uplift that may continue for millions of years, despite the absence of nearby plate collisions. Rather than requiring new mountain-building events, the surface rises because the weight pulling it downward has been reduced. Several seismic images beneath the central Appalachians appear consistent with this possibility. Regions showing slower seismic wave speeds may indicate warmer mantle replacing denser material that has already descended. Nearby zones exhibiting faster wave speeds could represent the detached fragments continuing their journey deeper into Earth's interior. Although scientists continue debating the precise interpretation of these images, the overall pattern suggests the mantle beneath the Appalachians is far more complex than once believed. At the same time, another process works in the opposite direction. Even as buoyancy increases in certain locations, erosion relentlessly removes enormous quantities of rock from mountain slopes. Every river flowing east toward the Atlantic Ocean or west toward the Mississippi River system carries tiny fragments of the Appalachians downstream. Individual grains of sand appear insignificant, but multiplied across hundreds of rivers over hundreds of millions of years, the total amount removed becomes astonishing. Geologists estimate that the original Appalachian Mountains may once have rivaled the world's tallest mountain ranges. Some reconstructions suggest elevations comparable to modern Himalayan peaks, possibly exceeding 5 miles, or roughly 8 kilometers, above sea level in certain regions before erosion gradually reduced them. Removing such extraordinary volumes of rock also changes the balance of forces acting within the crust. Imagine carving away the top of a floating block of wood. Because weight has been removed, the block rises slightly within the water. Earth's crust behaves similarly over geological time. As erosion strips material from mountain peaks, the crust slowly rebounds upward through a process known as isostatic compensation. This rebound does not restore every inch removed by erosion, because the crust and mantle possess different densities. Nevertheless, a significant portion of the lost elevation can be replaced through uplift generated simply by unloading the surface. That means erosion, which appears to destroy mountains, can simultaneously contribute to keeping them elevated. Scientists increasingly believe this delicate balance has operated across the Appalachians for tens of millions of years. Rivers cut downward into bedrock, transporting sediment toward the Atlantic coastal plain and the Gulf Coast. As weight disappears from the mountains, deeper rocks slowly rise to replace material removed above. The cycle resembles a slow geological conveyor belt, operating almost invisibly across immense spans of time. Yet, another factor complicates the picture. The eastern edge of North America borders the Atlantic Ocean, where enormous accumulations of sediment have collected since the breakup of Pangaea. Rivers draining the Appalachians have deposited layer upon layer of sand, mud, and gravel onto the continental margin. Some sedimentary basins offshore now contain deposits several miles or several kilometers thick. Transporting that much material from one location to another redistributes Earth's mass. As mountains lose weight through erosion, offshore basins gain weight from accumulating sediments. The crust responds to both changes. Mountain regions tend to rebound, while sediment-filled basins experience increased loading that promotes subsidence. This relationship creates a connected geological system extending far beyond the visible mountain chain. Every grain carried downstream subtly influences crustal movements across an entire continental margin. Satellite measurements have become indispensable for detecting these minute changes. Networks of continuously operating global positioning system receivers can measure vertical movements with astonishing precision, often within fractions of an inch or mere millimeters. Data collected over many years reveal that the eastern United States does not move uniformly. Instead, neighboring areas display slightly different rates of uplift or subsidence. These differences may appear trivial on annual timescales. A rise of only 1 millimeter each year amounts to less than the thickness of a credit card. Over 1 million years, however, that same rate produces approximately 3,300 feet, or about 1,000 meters, of cumulative vertical motion if maintained consistently. Nature rarely maintains perfectly constant rates over such enormous intervals, but the calculation illustrates why geologists pay close attention to movements almost impossible to notice during a single human lifetime. Researchers have also examined river systems for clues. Rivers naturally seek efficient paths towards sea level. If land rises, rivers often respond by cutting deeper valleys. If land sinks, sediment may accumulate instead. Many Appalachian rivers display terraces, abandoned floodplains, and deeply incised channels, suggesting repeated adjustments to changing elevations over millions of years. Some river profiles contain abrupt changes in slope, known as nick points. These features can migrate upstream over time, recording episodes of uplift that occurred long after the original mountains formed. Their presence across portions of the Appalachians has added another line of evidence indicating that vertical movements have continued well into relatively recent geological history. Not every scientist agrees on the exact cause behind every observed feature. Some emphasize mantle flow as the dominant mechanism. Others argue erosion-driven rebound explains much of the uplift. Additional researchers highlight the influence of glacial isostatic adjustment, ancient faults inherited from continental collisions, or slow deformation within the continental interior itself. Rather than competing explanations, these mechanisms may all contribute in varying proportions depending on location. The northern Appalachians, influenced more strongly by the immense ice sheets of the last ice age, may experience different vertical motions than the southern Appalachians, where glacial effects were much weaker. Similarly, areas underlain by thicker lithosphere may respond differently from regions where ancient mantle roots have already detached. This emerging picture transforms the Appalachians from a seemingly static mountain range into a remarkably dynamic geological laboratory. Every ridge, valley, river, and seismic signal reflects the combined influence of events spanning hundreds of millions of years, from the birth of a supercontinent to the slow circulation of Earth's mantle continuing far below the forests and towns of the eastern United States. Instead of marking the end of mountain evolution, the Appalachians demonstrate that even Earth's oldest ranges can remain responsive to forces operating deep within the planet. rising and sinking at the same time is no longer viewed as a contradiction. It is becoming one of the clearest signs that multiple geological engines, some acting from above through erosion and others from far below through mantle dynamics, continue shaping one of North America's most iconic landscapes.